is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms? You come to terms with this idea. Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And that is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light, and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed. And so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object, something that we can test and we can measure and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work? And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.
So, astronomy is not something that you do just from your desk. In many cases, you have to embark in an expedition. And 2 years ago, a large team of astronomers embarked in expeditions to the most remote places on Earth, in places where the atmosphere is thin and dry, because we need to observe at a wavelength where the atmosphere is important. The important thing of that is, in these locations are also facilities. As you see, they are like Iran 30-meter telescope or ALMA or APEX with European technology. And in these telescopes, the team of astronomers went there prepared with one eye into the weather forecast, checking up all the systems of the telescopes, checking that everything works, and waiting for the go command when the weather was good in all these sites around the Earth. One of the tricks you need to make such an image of a black hole is to get a telescope as big as the Earth. And to get that, the small pieces of this telescope are parabolic antennas, which you can see the locations in the picture there. These teams were observing that. We had a fantastic good luck because we get good weather all across the globe at the locations of the telescopes. These data were stored in disks because you don't have optical fibers there. You have to fill boxes of hard disks, pack them into an airplane, in some cases waiting for several months, like in the South Pole, until the winter over is gone, because it was night in April 2017. You weigh them, and these data are sent to processing centers where they are played back as they were recorded and synchronized with atomic clocks. These places are like in the Haystack Observatory in Massachusetts in the US, or in Bonn, Max Planck Institute. They are the so-called correlators. Data are played back, they are evaluated, and then they are given to a further team who checks this data. Every telescope is different. You need to correct for the characteristics of each telescope, put all that together so that you get a telescope as large as the Earth. And this process needed also several months of hard work, assessment, iterations, until people were sure, okay, this is the data that now we can begin to image. We can extract the information from this precious data, which occupy 6 cubic meters of disk, as I said, to get something like the image you have just seen now. And to know how you extract this information and you get from that, my colleague Monika Mosiwrocka will show us.
You may wonder how this image was made in the first place. Event Horizon Telescope data is like incomplete puzzle set. We actually only see pieces of the real true image. And then we have to fill in these gaps of these missing pieces to construct the physically possible image that is actually matching our data. This is actually a very difficult process. Therefore, the imaging process has been split into several phases. At first, at the very beginning, we were working on this imaging completely alone, each of us. This was a remarkable, almost life-changing experience to see an image of a black hole shadow popping out on the screens of our ordinary laptops. Next, we formed independent teams that worked completely independent from each other to repeat the imaging process. This was very necessary, important step because we wanted to get rid of the human bias as much as possible. And in the last phase, which took the longest time, the imaging was done very, very carefully via very careful scientific analysis. So what have we learned from the images, and not just from the images, also from the data that are lying underneath this image? So first of all, we have observed this source for 4 days. Over the 4 days, the ring is there. The image looks almost exactly the same. We have also measured the size of this ring. Over 4 days, the size is always the same. It doesn't change. We have also measured the contrast between the ring itself and the central darkness. And the contrast is as large as it is expected for the black hole shadow. But there's one more very peculiar thing about this ring. It's not really a full ring. It actually is much brighter at the bottom side. Why is that? Our models told us immediately that this kind of structure can be only formed if something in the source is rotating. What is rotating? It could be the black hole, but also the matter around it, or both can be rotating. At the moment, the images are not yet sharp enough to actually estimate or calculate the exact speed of this rotation, but these images give us a sense of the direction of the rotation, which is clockwise in the sky. So to summarize, our images, our data tell us that we are looking at the shadow of the black hole, which has been predicted by all the models of the black holes that we have developed over the last few decades. And now Anton Zenzus will share some final remarks on the current state and the future of the Event Horizon Telescope. Thank you.
So my job now is to put it all together for you. The Event Horizon Telescope is a very ambitious project, but one with a very clear goal. We want to image, for the first time, the central black holes in the galaxy M87 and in the Milky Way. Today, now, 6 papers are appearing in the Astrophysical Journal Letters, a special edition, that show the image and all the discussion that is needed to convince our scientific colleagues. And in a few days, the data from our observations will be made public, so that scientists anywhere in the world can verify our results. So how have we made this happen? We had to assemble a fleet, a capable fleet of the best and most sensitive millimeter wave radio telescopes in the world, combined the supercomputers to form one large radio telescope. We had to organize a team that now numbers to more than 200 scientists from many institutions around the world. This is a truly global collaboration. We cannot name all the people that are participating in this, but representative for all of them, I want to recognize Colin Lonsdale, Director of Haystack Observatory, and together with me, co-chair of the EHT Collaboration Board. He represents, together with our other friends here, the global partnership that we have, all the people that now are listening elsewhere that work together in this project. The preparation for these observations took a long time. I've spoken this morning to somebody who started 40 years ago building sub-millimeter telescopes. And so you can say several decades of preparation went into what in 2017 was for the team a very, very difficult, a complicated experiment to perform. This experiment was